Let's take a look at example 5.11, which asks us to describe a region as type 1 or type 2. We're told to consider a region in the first quadrant between the functions y equals root x and y equals x cubed. Now, just for reference, we should think about what these graphs look like. So root x looks a little bit like that, and then y equals x cubed looks a little bit like that, roughly. So if we thought about how this graph would look as far as a region, the top portion would be carved out by the root x curve, and then the bottom portion would be carved out by the x cubed curve. So this would be our region. And just with the way that I described it, top carved out by this function, bottom carved out by this function, you would probably easily believe like, oh, this is a vertical region because we have a top and a bottom function. And you'd be right, we could easily describe this as a type 1 region. I'm going to start off first by writing up the piecewise function, where I know y is going to be between two things and x will also be between two things. The y values are squeezed between the bottom and the top function. So the lower you are, the smaller the y value, therefore x cubed is our lower bound for y. And then the higher up you are in the region, the larger the y value, therefore the upper region or upper bound for y would be root x. Now this is what I was referring to in the last video. It's a little bit odd to ask, what's the smallest value you can have for y? And the answer is x cubed. And that feels strange, but if you look at the picture, you can make sense of the fact that the function x cubed is defining the y values along the bottom portion of our region. Okay, once we have our y values squeezed between these two functions, we can talk about the x values. Now, in a type 1 region, we're drawing vertical lines starting at the smallest x value and going all the way up to the largest x value. So we need to find those intersection points. We need to know where the square root x and x cubed function intersect, because those 2 points mark the left and right endpoints of our region. So the easiest way to do this is to say we want to know where these two functions intersect each other. We're essentially just solving a system of equations here. Since both of these are equal to y, we can just set the two equations equal and solve here. I can square both sides to get rid of my square root. Whoops, square goes on the other side. So then I have x equals x to the 6th. I could use the 6th root to try and solve this, but we would just end up going back and forth. I can't divide by x because, well, we could. Let's see, if we did try to divide by x, we'd have to consider two cases. We don't know what x is, and if x happens to be 0, then this is illegal. However, before dividing by 0, if we were to find out x were equal to 0, then that the equation would be true, would be solved. 0 is equal to 0 raised to the 6th power. So x equals 0 is one solution. The other case would be, all right, what if x isn't equal to 0? Well, if it's not, then I am allowed to divide by x. That equation would become 1 equals x to the 5th. We could take the 5th root of both sides and we would find x equals 1. So we have two solutions, x equals 0 and we have x equals 1. X equals 0 is our left endpoint, x equals 1 is our right endpoint, and that's what we'll put into our piecewise function to describe the region. So when it's asking for a description of the region, writing these inequalities would be perfectly acceptable. Next, it says to describe it as a type 2. Type 2 region, we need to kind of shift our thinking. Instead of saying we have a top and a bottom function, we need to re-evaluate this region and consider it a left and a right function. So I'm going to copy our drawing. I'm going to try and make it exaggerated a little bit so that we can see what's going on a little better. Now that top function, we said that it was the y equals root x function. But what if we did a little bit of algebra and rewrote that as an x equals function? So instead of y equals root x, what if we square both sides? Then we'd get y squared equals x. And technically it's plus or minus, but we're working in quadrant 1, so we're only going to keep the positive version. So we have y squared is the function that we are going to consider on top. And this is more like the right function. So if we were to consider horizontal lines in our region, every horizontal line is between a left and a right function. And I realize I just said right, but I meant to say left. This would be our left function, x equals y squared. The right function is the y equals x cubed, but we need to reevaluate the way we're looking at that function. We need to solve it for x. So then that would become the cube root of y. So then the right function is going to be x equals cube root of y. So in a type 2 region, when we set up our inequality, and we say y has to be between a small and a big range, and same for x. This time the x values are going to be squeezed between the two functions we found. So the farther left you go, the smaller x is. That would give us the y squared function. The farther right you go, the larger x is, so that would give us the cube root of y. And again, notice that x is being defined between the ranges of y squared and cube root of y. So we have y's telling us how small x can be. And now we have to think about the y values that these horizontal strips are going between. It is still these intersection points, but last time we used the x values of those intersection points. This time we need the y values of those intersection points. We could just simply set our equations for the left and right bounds equal to each other, just like we did before. That would say y squared is equal to the cube root of y, and we can solve this the same way we did with x's. So I'm going to cube both sides so that I have y to the 6th power equals y. And we know that there's two possibilities, either y equals 0 or it does not. If y equals 0, the equation is solved. 0 to the 6th power is still equal to 0. And if y is not equal to 0, then we can divide this down and we'll find that y equals 1 is a solution. Now, it is a little bit fishy that the x values that were found in the type 1 version of this region are almost identical to the y values. Don't depend on that. It's not always true. It just happens that there's some symmetry in this problem that was a happy coincidence. But hopefully watching this example, you're able to see both ways to describe a region. Now, this region is special in the fact that it can be either type 1 or type 2, but in the next couple of examples, we'll see that's not always the case.